For today, we have 3 points to discuss. The first one is problem about cars and wagons. Second one is about a rectangle. Inscribed in a curve. And the third topic will be about mirrors and phase spaces of mirror system. Andrei will talk about that. So that's a plan for today. I hope we will be able to take out all the points. So let's start from the problem about cars and wagons. So I'll just tell you like the way to solve it without maybe some without going too deep in the solution. So just a sketch, I would say. So we have two towns, let's say A and B, and we have two roads, and they can go like, wait, sorry. They can self-intersect, for example. It can be any shape. So we have two roads. Okay, good. And we know what? Two cars went from A to B, let's say, and they were connected by a rope. And I think the length of the rope is less than what? Than 10 meters? Yeah, good. And the question is, if we have two wagons, and they're like weird round wagons, going in an opposite directions, with the radius with the radius more equal than 12 meters. Please correct me if I'm wrong. I might forget the numbers.
I think
so
the
check.
sum of the radius is more than 12 meters. So each of the radius is more than 6 meters.
Oh, yeah, of course. So I read two radius is nice. So, and the question is it possible for wagons to go this way without colliding? And let's do the following. We will do a parameterization for every road. For example, for green road from A to B, we identify this green road with a line segment from 0 to, let's say, L1 to be the first road. And the second road also from A to B. We identify it with a line segment from 0 to L2, let's say. So L1 and L2 are the lengths of our roads, of course. So what? How does a phase space should look like in this case? And well, phase space for two vehicles moving along this road. Probably participants have some ideas. Oh, I just drew an answer. Anyway, it's a rectangle. So here is 0, here is L1, here is 0 for the second road, and L2 is here. So let's see. The cars, I'll draw them in pink. They go in the same direction. So they start here from A. So both car on green road, a car on red road start at A and they go to B. And so, for example, this point means that car on the green road is here and car on the red road is here, for example. So our horizontal axis parameterizes the green road and our vertical axis parameterizes the red road. Yes, and the wagons, they go the different way. I'll draw them in blue. So the starting point is when, well, let's say the first wagon on the red road is at A, and the second wagon on the green road is at B. So that means that on horizontal axis, the coordinate is L1, and on our vertical axis, coordinate is 0, and they go, well, they swap basically. So they can go like this. So at this point, let's see, the wagon which goes along the red road is at point B, and the wagon which goes along the green road is at point, well, A. And if there is an intersection point, what does it mean? You see our two curves intersect. What does it mean in terms of our problem? Any suggestions? Okay, are you here, guys? It's just so quiet. It's yeah, it's scary a little bit. Okay. It basically means that at some point of time, cars and wagons, on some different points of time, of course, cars and wagons were at the same positions. So let's say here. And this means that the distance between these positions is less than 10 meters because of the cars. So there is no way that two circular wagons with radius 6 meters each can pass over each other. So there is 6 meters, there is 6 meters. They will collide definitely. But as we discussed on the previous seminar, it might be hard to prove this fact for just, now we have some arbitrary continuous curves in our figure. So it might be hard to prove this fact just working with continuous curves. So we go a step back and let's say we have polygonal curves. And the fact that if we connect opposite angles of some rectangle by polygonal curves, then these curves will intersect actually in an odd number of points. It is easy to prove. Well, not like easy, but it's easier than the continuous conjecture. And then the thing we can do is we can approximate our continuous curves by polygonal curves. What will we do? We will just draw some points on each curve. And then we will connect these points by line segments. And the aim is to draw these points in such a way that these line segments were not far from the curve. So I mean, if I have a line segment, and this is some piece of curve, what I want is the distance between these two entities are pretty small. Well, this way we can approximate both of our continuous curves. And we can make these approximations better and better by trying to make this distance smaller and smaller. And each time we will get an intersection point, actually. Well, we might get, for some curves, we might get several intersection points. Let's see. For example, we can go and then like this and like this. And we have 1, 2, 3, 4, 5 intersection points. So actually, and these curves, these continuous curves might go in a weird ways. But when we get these intersection points by, well, lessening the distance between continuous curve and polygonal curve, we will get a set of points, intersection points inside our rectangle. And there will be infinitely many points because we can lessen the distance infinitely many times. And because these points are inside the rectangle, we get that these points will dense up will dense up to some point. So let's say there is maybe not that much of them. And the point to where they tend to go as we lessen the distance, this is actually our intersection points of the continuous curves. So, yep, that's how one can prove that Huygens cannot pass each other without collision, or sketch of the proof, because please look at our PDF file for more details. We have a more rigor proof there. Do you have any questions? Or maybe my colleagues want to add something to this part?
I can add something to when we have to prove that the polygonal lines have an intersection points. We do this as follows. We suppose that the polygonal lines are in general positions, and then if they are, then the intersection, the number of the intersection points is odd. So to prove that this number is non-zero, we just prove that it is odd.
Yeah, actually, this assumption about general position, as Andrei said, is crucial for our proof. But if we have some curve, which is polygonal curve, which is not in general position, we can tweak it a little bit to make it be in general position, actually. Well, please look to a PDF file. There is a lot of little convenient conjectures that will help you to understand this proof. Any questions? So I'll just move to our next point. And it's about inscribed rectangle. So suppose we have some continuous curve in the plane. And the aim is to prove that one can inscribe a rectangle to this curve. So I'll try to do this. So maybe this way. Oh, let's say that's a rectangle. Looks pretty fair. There are actually two more interesting results. They were proven like recently that actually you can inscribe a square and you can inscribe, well, I think a rectangle with a given ratio of its edges. But these results are quite hard to prove, and it's easier to prove that you can just inscribe some rectangle. So let's see how it goes. At first, let's notice that if I connect opposite corners of my rectangle, I get two equal line segments. So let's say it's A, B, C, D, and this point is O. So I get two equal line segments. And or is the middle point. So AO equals OC and DO equals OB. And basically, if we do the opposite, if we manage to find such line segments that at first the length is equal and the point of intersection divides them into two halves equally, and actually these 4 points form a rectangle from obvious geometrical properties. So we don't need to search for a rectangle. We actually need to search for two similar line segments which intersect, and the point of intersection divides in halves. So let's see, if we want to look for a line segment, we can do, well, we need a configurational space for pairs of points on our curve. And you can notice that, well, we parameterized rods in a previous problem by line segments, and we can do the same thing for a curve. We can parameterize it by a circle, actually. So for example, this is, I don't know, point P corresponds to point P here. And then these 2 points correspond to these 2 points. So now we can work with a circle. It's easier than working with the arbitrary continuous curve. So how does the phase space, the configurational space of pairs of points in a circle look like? Let's try to understand it. I can identify a circle actually with a line segments from 0 to 2 pi. And not just the segment. I actually need to glue together these ends of this segment. So I say identify a circle with a segment, but this end and this end, they are actually the same point. So I glue them together. And as long as we need pairs of points, well, as you might guess, we will get, well, let's say that's one copy of our line segment, and that's the second copy of our line segment. Here's 0, here's 2 pi, and here's 2 pi again. But there is one catch. As you can see, points on our line segment are ordered. So you can say which is the rightmost and which is the leftmost. But when you look at the circle, you can't really tell which point is what. So let's say that, let's call this segment X, this segment Y. So let's say we will consider just points where X less or equals than Y. This will eliminate, well, for example, this is point A, this is point B. And the second situation where this is point B, this is point A, they're actually the same on the circle. So this equation will eliminate such situations. So now let's draw this on our cute little picture. So this is X equals Y. And I need to, well, to shade where X is less or equal than Y. I think it's here. Please check. So I'm interested in this shaded region. But that's not all. Actually, let's see. Well, this point at 0, 0, and this point at 2 pi and 2 pi, they are the same point. So this is the place where we glued our line segment. So basically what we need to do, we need to glue together this side, and let's see, I think this side. So this point goes to this point goes to this point, and so forth. So basically it goes here and it goes here, and it's kind of hard to understand how to take a triangle. You can actually try it at home, take a piece of paper, cut off a triangle, and try to understand. I can't just fold it and glue these sides together because I need an opposite orientation. So the next trick would be the following. At first, I'll cut my triangle here. Oh, sorry. Okay. This is a part of a second diagonal. So I'll cut it here. Then I will glue red parts together, and then I will glue green parts back together. So let's see. When I cut it by this green line and glue together red parts, I get, well, a square. Yep. Okay, which color is it? So I think it's this color. Here is my red, red segments glued together. What I need to do, I need to glue these segments together, because this is our green segments to which I cut the triangle. And when you can do, I remind you, you can do this experiment at home. So when you glue these parts back together this way, actually this segment and this segment should be glued in opposite orientation. So you twist and glue. And basically what you get is you get a Möbius strip. Möbius? I think it spells this way. I'm not sure, please check. Möbius strip. Good. So now we know that our pairs of points, well, let's say our pairs of points on the curve correspond to the phase space of pairs of points on the curve correspond to a Möbius strip. Okay, now one more mental effort. Now, what we're gonna do? Well, when we try to find the required line segments here to form a rectangle, we actually need to find, well, line segments with two properties, equal length and intersects divided into by points of intersection. But how to track these properties? The idea is the following. So let's say we have plane and we draw our curve in that plane. And when we take a pair of points, what we're gonna do? We're gonna find a middle point of this line segment. That's a step one. Then we will measure the length of a line segment. That's a step two. And then we will draw a perpendicular segment. Well, for example, in upper semispace. And the length of this orange segment should be equal to the length of this black segment. And we say that for this pair of points, this point corresponds to. So I take a pair of points and I get by this construction a new point in space. So basically what I did, I took some point, let's say I took some point on a Möbius strip, because we know that pairs of points on our curve correspond to points on Möbius strip. So I took some point on Möbius strip and identified with some point in space. And when we find the required line segments, how would it look like? Actually, we have one black line segment, and the second one, it will correspond to the same point. So basically, we have two different pairs of points which correspond to the same point in space. So let's see. And well, one more note, points on the edge of a Möbius strip correspond to points on the curve. So, I mean, you have, it's like a line segment of zero length. So when two endpoints are the same, and the length of such segment is zero, so the point in space corresponding to it is just this point. So all points from the edge of a Möbius strip, they go to our curve here. So the picture you should imagine is you just glue the edge of the Möbius strip to this curve, and then the surface of a Möbius strip is in the upper semispace, just, being there. And well, the crucial point in solution for this problem is actually when you do such map from Möbius strip to R3 to space. It's called embedding, and the thing is, this weird surface above our continuous curve will self-intersect. And actually, self-intersection is what we are looking for, because self-intersection means there are two line segments which correspond to the same point in space, and that means that their centers are in the same point and their lengths are similar, equivalent. Yes.
This map from M to R3 will be not embedding.
Oh, yeah. Of course, because embedding means that different points from M goes to, sure. goes to different points from space. Of course, not embedding. Sorry. Yeah, you're absolutely
So
right.
in the project, we have proved that there is no such an embedding. And this fact is pure topological. Okay.
Yeah, I think there are some techniques from topology used to prove this fact, but they are definitely accessible for students. It's a good exercise to look carefully through our solutions and try to understand every point of it. Do you have any questions, or probably my colleagues want to add something?
I just have a question regarding the inscribed square.
Yep.
I can't find anything online. I mean, because I knew that it was unproved a couple of time ago, but is it proved now, or because I can't find anything online, it still says it's open?
I think it was proved.
Yeah, very recently.
Yeah,
So,
but we have not this article. We can find it and send to the MetaMost. Okay.
yeah, we will find this paper and send it to you, to all of you.
Okay, thank you.
I think it was proved like last year or something. Probably someone get very bored at quarantine. Okay, any more questions? How much time do we have actually? Can someone tell me?
I think we have no time at all.
Uh-oh.
The next project will start in 5 minutes. So we have a 5-minute break, I think.
Oh yeah, so we didn't get to mirror stuff, unfortunately. But probably we can assemble seminars sometime later after the conference. I don't know. That depends on Andrei. Okay, so thank you all for coming. Thank you all for submitting your solutions. I think it was interesting to read. And if you don't have any more questions, we go on a break. The next project will start the seminar in 2:30 Moscow time. So it's actually 3 minutes left.